Well, hello everyone. Good morning, good afternoon, good evening from wherever you're joining us from. My name is Dalia, and I'm the Senior Global Community Manager here at Kong. I'm very happy to have you here at our user call today. Let me just move screens so I can see better. So today we are here with Patrick Huck, who is not only a senior computing engineer and physicist at the Berkeley Lab, but he's also one of our awesome Kong champions. So I'm very happy to have him here today. We are here today to talk about the transforming DevOps for scientific innovation, and more specifically, we were going to talk about the Materials Project cloud native journey to 500,000 user base. We will also learn what part Kong had to play in the Materials Project journey and how they used to manage, access, and control traffic to its services. So this webinar is being recorded. We will share the recording right after in an email with the slides and some blog posts for you to take a look on. We will also upload the recording to our YouTube page, to our YouTube channel. I will share the link in the chat here so you can also view it there. Patrick, please take it away from here.
Thank you, Dalia. Thank you for having me. Very happy to talk here today. As Dalia said in the introduction, I'm trying to make a case today for how the Materials Project transformed its development and operations for, particularly for scientific innovation. We've been a project that's been around for over 10 years now, and have reached 500,000 users recently. I'll start by kind of introducing what the Materials Project is a little bit, then talk about how our metrics have changed over the years, then how we implemented our architecture in the cloud from previously something that was on-prem on high-performance compute clusters, and then move towards what the role that Kong plays and how we do unified observability across our stack. So it'll be a little bit of a narrative of how these things play together and how they've actually held up for over 3 years now to get us to this point. Materials Project started in 2011 as a Materials Genome Initiative from the White House. That Materials Genome Initiative is still around, and we are a key player in this. The whole goal of that initiative was to make materials design faster, less expensive, and more predictable. The Materials Project, particularly then, uses supercomputing and state-of-the-art methods to provide information about materials through our website and through API. All of this is computed information. Before the Materials Project started out, it was it all kind of material science in general went the Edisonian approach, saying like, I would try to make a material with specific properties in the lab. I would characterize it. I would try to measure its properties, and I would see if they come out the way I want them for our application that I'm interested in, and if not, I throw it away, and then I keep doing this until finally find a material that hopefully is a good fit for my application. That has changed with the advent of Materials Project, and it introduced a little bit of a paradigm shift to now take all the candidates of structures, crystal structures in this case, compute their electronic properties from first principles, and then throw away through screening what might not fit my application, hopefully get a list of materials that are better fitting and that might be synthesizable in the lab, and then go through that same process and find that quicker. So that's been the overall mission of the Materials Project in the last 10 years. What does that look like in practice a little bit more? We have a database of inorganic crystalline material structures and their electronic properties. We accelerate materials discovery through the development of advanced scientific computing methods. So the research group of the Materials Project is focused on delivering science with the technology that we develop, and then I'm on the technology side, working on the dissemination, scaling computations to to all the inorganic compounds that are out there, and then develop tools that we can provide to the larger materials community. On the right, you can see how a researcher that would come to the Materials Project would use our data to do science. They could take all the structures that we have available on our platform, apply a few screening criteria on the properties that we calculate for these structures, boil them down to 10 or 200 candidates, check them out in the lab, or then even close the loop and say, hey, we could take those candidates, maybe put that into machine learning algorithms, train them a little better, and come up with new candidates that we could screen through this funnel, and that way basically close the cycle between computed theoretical predictions and experimental measurements. A little bit more about what our interface looks like. So there's basically two aspects to this. On materialsproject.org, you get the interactive access to all our data, and you also get programmatic access. On the right, interactive access is basically split into our main application, which is the Materials Explorer. So you can choose chemical systems, elements. You can filter by the properties that we calculated and their values, and this gives you a list of materials that could be interesting for the application that you're looking at. But then we also have, you can see this on the left here, we have dedicated analysis apps that focus on certain aspects of our data, like phase diagrams, Propay diagrams, interface reactions, absorption spectra. We also have dedicated explorers that look at certain data sets that are interesting for synthesis or catalysis or metal alkaline framework. So it spans a wide class of materials that we're serving, and that's kind of part of the that organization, and the depth in properties and materials classes that we're covering is part of the success and the growth of Materials Project. And then on the programmatic side, we have an API client. We have an API, of course, that's a REST API, and we provide a Python client for it that we call MP-Rester, and then people can just go and search all our properties and calculations, and people go actually and develop secondary apps that are based on MP, or they write a lot of papers based on the data that they get from Materials Project. I think at this point we're getting cited at about 3.5 times a day. So it's Materials Project has become a pretty integral part of the overall materials science research in the world. Just kind of giving you an additional overlook over what the properties are. That's as I said, there's a pretty deep list of calculations that are and properties that are being calculated. Developing the workflows for this long list of properties is what scientists in our group and postdocs and grad students work on. Like each of them are multitude of papers and PhD students and postdocs that have invested their work in it, and then published workflows that we as Materials Project can run in a high throughput scale across all our structures and calculate these properties. So you can see this is a visualization of a crystal tool, of a crystal structure. All of this is based on Plotly Dash, which is a visualization framework that allows users to write apps in Python. So every element on the page, when it gets updated, is basically sending an HTTP request back to the backend server that knows how to render this piece of the website. And that paradigm allows an environment like us, where we have a small engineering team, but a larger group of scientists that are using the platform, to also allow the scientists to help us develop. So a lot of the some of the apps that you see are actually developed by the community, and we integrate that into our stack. So just kind of going quickly through what this looks like. We have visualization for thermodynamic stability, electronic structure. All of this is interactive, and it's a pretty wide list of properties that are applicable in different applications: equations of state, X-ray absorption spectra, charge densities. So without even knowing what those things necessarily are, but you can see that serving the data for this in a reliable way and making this performant is a challenge. The one aspect also that the Materials Project as a platform provides is that users in the community can contribute their own data. So we've also become a data management platform for the wider research community. Okay, how has Materials Project developed over the last 2 years? When I joined in 2014, around here, we were 2 or 3 years into our journey, and then about 5,000 users. And since then, we have exploded to over 500,000 users by the end of last year. We went through the transition of, as I said, on-prem infrastructure to in the cloud infrastructure towards the end of 2021, early 2022 is when we actually switched to Flip. So that has been kind of a journey that started in mid 2019, took a couple of years to microservice our infrastructure, come up with the suitable cloud infrastructure, and then actually make the switch for serving that worldwide and retire our monolithic legacy website. And you can see those two, overall user growth is in blue. Our legacy website that we've still kept up over the years for some backup functionalities that some people still use. It has kind of flattened out, and then our new website just has been catching up. At this point, when we made the switch in early 2022, we had about 265,000 users. We're already well past this now in our new infrastructure alone, and we've doubled our user base since then. The inlet kind of shows the growth that we've had. We're still growing exponentially. We've had 4 quarters in a row where we had more than 35,000 accounts signing up, but the most recent quarter actually jumped to 43,000 accounts. So we haven't seen a flattening trend at all in our user base. The reason I say these things as I get into using Kong and using Datadog is that, and using AWS, that this is still based on an infrastructure that we architected 3-4 years ago and is running just fine. I think that's a good message to take away from this. Our project is worldwide, right? So this is our user base since 2023. We had over 232,000 unique users from 178 different countries. You'll see by the end of my talk why that is impressive, because we are only 4 staff engineers with our principal investigator and the research group, and with the budget of a DOE core program that is much less than what other tech startups usually have, we were able to provide this. We served in the last year over 300 million API requests that transferred 32 terabyte of data. That is only through API. So we have we have more repositories in AWS Open Data. I'm going to go into that later, that serve 10 times as much data. So we are in the order of 4, 5, 6 terabytes a month at least that our users download from our services. Of course, China and USA are our top users in that regard, but on a per capita basis, Europe and the USA and the US are leading by far. A little bit more about our apps and how that's grown. There's a part on our website where you can be authenticated. That's where Kong comes in later to see more information, or you can look at some of it anonymously. That helps with search engines and discoverability of our data. Our apps are visited 52,000 times every month, and that creates 164,000 authenticated page views. When I say page view, that is rendering all the properties that I've shown you in one of the previous slides, and loading all these graphs and people looking at that. The majority is the Materials Explorer, but our other analysis apps are pretty popular too, especially the phase diagram app that drills into phase properties of materials. And then in terms of active users, we're in the, you can see we're in the 40K, around 40K every month, around 13K every week, and then around 4K every day. And that's been solid for the last year. You can see a slight upward trend, but you can also see the dips when the world or researchers go into holidays. So this would be around Christmas, and this would be about Chinese New Year. So, and you can see the last dip here too. So this gives me the confidence that this is real traffic and real users. All right, let's dig a little deeper and see how things work in Materials Project in general. As I said, we have workflow softwares that set up the computation on high performance compute to do simulations needed to come up with those properties. There's a very widely used analysis package, PyMagen, that has been the leading material science analysis package in the world for the last decade, I would say. And then there's what we call builders that take data that comes out of these calculations and out of these workflows and builds them into what the website and the API needs. We rely on open source development in GitHub. Everything we do is open source. All our data is open data. And then we deploy continuous cloud deployments using Dockerized containers, and that guarantee quite a good uptime for us. So our uptime has been, I think, 99.98% in the last year, so less than 2 hours of downtime. And we also rely on compute centers at the Department of Energy compute facilities for these calculations, and then a lot of these calculations get transferred and built into a managed MongoDB and Atlas that then sits behind the website and the API. Together with our open data repositories on AWS and the sponsorship that we have there, and the Office of Technological and Information in the DOE, we became a pure data resource, which means we are good stewards of data. We are the only project that has that designation in the material sciences. There's other databases out there like the Particle Data Group that have that same designation. In terms of infrastructure as code and how we've made this transition, it's a pretty standard setup in terms of enabling continuous cloud deployment. So it all starts with a push to our Git repositories. There's a dedicated development and operations repository that ties together the different repositories that make up our stack. So, as an example here, MP contribs, but there's also our web API, our web services, our API services, but also Kong. So all of this applies to every service that we deploy. The template then goes ahead and builds our VPC, sets up our network load balancer, our SQL databases that we need behind Kong. If there are any updates to any of these resources, these go through, tracked updates to these resource definitions in the CloudFormation templates. Then the pipeline goes ahead and builds all the images for all the services. That includes Kong. And that's based on Docker. And once we have these images for the different services, we push them to the ECR repository on AWS and deploy to Fargate and ECS. Excuse me. That deployment stage is automated in the sense that these images are pulled and the number of tasks is set up depending on the definition and the requirements. We also set up auto scaling rules and security groups and all of that. So that's what a kind of continuous deployment looks like on our end. We can dig a little deeper and look at our setup for the cloud resources and how a standard HTTP request would get through our resources. So say the internet is out here outside of Cloudflare. If you go to Materials Project, you first hit the Cloudflare Edge servers that do SSL termination. They also do defensive efforts of denial of service or blocking IP addresses that are doing abusive traffic. They also do IP-based rate limiting. So at this point, we don't have a sense of a user yet because we haven't reached Kong yet. Kong is what defines our consumers. Goes through an internet gateway and hits the network load balancer behind it. A lot of this connection is implemented with health checks. So there's continuously health checks going on to make sure that the servers that need to be up are running. And if not, those health checks will make sure to issue warnings or monitor and stuff. But it's It's a first line of defense between Cloudflare and the network load balancer to make sure our services are up. The second layer is in a public security group is Kong. We are currently running on just 2 nodes. That has been plenty for our traffic. And then Kong is in charge of routing traffic to our backend services. So, it says Django and Flasker here, but, now it's Plotly Dash and Fast API. So more modern platforms for writing web services and APIs. And, but it can also, Kong can also, connect to, the RDS database that we have in the background, Elasticache resources for caching responses and speeding up web services. This role of Kong is probably one of the most important in this whole stack, because it has also allowed our developers to focus on their concerns. So like, it's not the old paradigm of when I write an app, I have to also implement authentication. I have to make sure I secure everything. But since these services are containerized and run in private subnets, there's no way to get to the internet or to get to this private subnet other than through Kong. So that's a security posture that has worked for us. It also means that when you develop in here, you can't just access services outside of our cloud environment, but that has been more of a feature than a bug. And then Kong does multiple things. We use the ring balancer in Kong. I'll talk about it a little bit later to actually balance traffic between multiple of these versions and backend services in the private subnets. The data is, as I said, is mostly served through MongoDB. So we have our Atlas managed cluster, and that the API is the only thing that API server is the only thing that directly talks to our database through a peering connection in a view. So these two are tightly connected on a network level in the same US East 1 region. That setup, kind of keeping it within the same region, has also been very cost efficient and has allowed us to use these pieces without having to send traffic through the internet and then risk less reliability, less security, but also increased costs. And then a last piece I want to mention here is that observability across this entire stack of resources in the AWS cloud is managed or done with Datadog. So Datadog receives logs directly from Cloudflare, but it's also set up as sidecar containers in our backend services and next to Kong to send to receive data and to set up health checks, monitor health checks, set up alerts, set up status pages. I'll have a little bit more about that later. I've talked about our continuous deployment pipeline, a little bit of what that looked like, and the different stages in an earlier slide. This is kind of drilling into it a little bit more, and also the way that we deploy Kong. Again, it's setting up a clone from our DevOps GitHub repository. It updates and deploys the base resources such as the RDS and Elasticache and VPCs and all of that. It separately builds all our images, pushes them to ECR. And then the two deciding steps in this deployment procedure is first scale up tasks and deploy the internal backend services that are sitting behind Kong in private subnets, and then deploy or update Kong. This step to kind of deploy and update Kong doesn't always need to happen. But as I said, since our private backend services sit behind Kong, the strategy of updating and flipping them into production are different. The Kong endpoint, if I go back, or the Kong service sits right behind the network load balancer. So that's more of an AWS deployment strategy. If I bring up Kong, I have to update the upstream targets of the network load balancer. So that's handled by Amazon ECS Blue Green. What it does is bring up a test stack with test traffic and test listeners for the network load balancer. I can test the traffic to Kong, and I can make sure that things are as they should be. And once things look good, I can make I can flip this around and bring the old stack down. So that's something that is handled within ECS. But then switching over to our new services is actually handled by Kong. So Kong has, as I said, we use the ring balancer. We use upstream targets to define the list of IP addresses where these services run in their separate subnets. And Kong just runs health checks against those IP addresses in those subnets and figures out which ones are the ones that are live. And once we update the configuration in Kong, we can basically flip the new services into production. I'll keep digging deeper. I've mentioned some of this on this slide already. All of what I've just said has in the past been described as the Kong way. Not sure that whether Kong still does it or not, but it kind of stuck with me. Kong way means there's Kong kind of takes care of a lot of the pieces of an HTTP request and pieces of a stack that don't need to be in a service, in an application that serves a certain purpose. So such things are authentication, looking at bots, doing cores, even sending metrics to Datadogs, imposing request size limits. So this is the kind of a selection of plugins that we are already using in Matthias' project and that has served us well. We also use the keyout plugins. In our case, that is for API keys. So users don't only have a login and an account on Matthias' project through their open authentication. They also get issued API keys that they can use in their Python client to make requests to Matthias' project API. We use access control lists to give certain people access to parts of the data. A good recent example of this is our collaboration with Google DeepMind. That data is under a different license than the data that we usually have. It's still open, but it's a slightly different license. And we ask people on the website to accept that license specifically, and only if they do, they will be put in an ACL group that allows them access through the API to that data. So depending in which group you are, you get a different set of data in the website and also in the API. I've talked earlier about rate limiting in Cloudflare. Cloudflare rate limiting in first order is IP-based. You can do things like header-based rate limiting, which in this case could be a consumer header from Kong. But we also use Kong on its own to limit specific callbacks on the website. So if a user is programmatically scraping our website, we would rate limit this here. And then the final piece of the puzzle is our custom OAuth plugin that basically connects the sessions in Kong with an OAuth proxy server. I'll get into that in a second. And then if we go into the backend, Kong upstreams all the IP addresses for the services in the private subnets are registered as upstreams in Kong. The ring balancer goes around those upstreams and updates the targets, and that way knows which IPs to and which ports to send traffic to. So for instance, in this case, this could be port 5000 in this private subnet, and the upstream and the targets for this upstream are defined such that Kong can find them and route traffic. So there's another set of health checks going on between these two layers. So a little bit about our Kong configuration. For our purposes, since we don't have a wide net of services that we need to run, it's only a handful. We manage all of that with DEC on a programmatic level, so declarative Kong tool. DEC also takes care of updating the configuration and do blue-green deployments when our new services are ready. And as I've mentioned previously, all our services are tagged. There's pieces in the Kong gateway that run next to each other, such like our login service, logins for emails, the authentication server on its own with the profile pages. So that's on the Kong level, but then there's also the backend services for our website and our API that are running in different private subnets, and they're defined as upstreams in Kong. And then when we want to go out and say, we have production running in private subnet 1, Kong would know to route traffic to this upstream. But as we would deploy the same services into 2. We would do our checks and would bring it up on a preview domain. We would let our principal investigators look at things, see if the data looks okay, and if it does, these 2 upstreams just switch role basically. All of that is handled with simple DEC commands. In terms of authentication and the role of users, we've defined users as separate consumers in Kong, particularly a combination of their login provider, so either GitHub, Portier is an email-based login provider, or Google or Microsoft or Amazon, the ones that we've enabled, together with their email address. So that makes different accounts in quotes on our in our Kong database. And the authentication for this, along with generating API keys, runs in a public subnet, as I've said, and the OAuth proxy server for it runs right next to it. So the Kong admin API and the OAuth server can communicate through localhost. So that has made, that complicates scaling potentially eventually a little bit if needed, but this hasn't been a problem. But it makes developing a lot easier since, some of those services run right next to each other. There is not much we have to do to additionally route traffic between different services. That same paradigm also applies when the web server wants to talk through the API. There's a separate API container spun up in each of the tasks that the web server can communicate to. So all of that is internal traffic. Want to dig a little bit deeper into the OAuth plugin that we've developed. Again, if you go to my GitHub account, we called it Kong Grant Proxy OAuth. It's been around for a while. It's not in a shape that I would say, I would push out there publicly right now. We've been lucky that we developed this under Kong 2.8 and that Kong has decided to have a long-term support for it. That has served us well to not have to yet go through the process of updating all of this and potentially reducing our output on the science side and on the other tech side. So this has been in production running for 3 years. So despite of not being documented as well as it could be, it's been a production tool for a while now. What the plugin specifically does is connect the Kong admin API and specifically the sessions in Kong through a OAuth proxy server. In this case, it's called Grant, developed by Simov. I actually don't know his full name, but this is a public proxy OAuth server that basically provides a layer between all the OAuth providers, Facebook, Amazon, you name it. It's like 200 providers that are enabled in Grant, and that interface is then, consistent across all these OAuth providers, and I can use that to enable certain a list of OAuth providers that we want to have. So we've enabled, we use GitHub, Google, Facebook, Microsoft, Amazon. They're all enabled and configured in Grant. And we also enabled logins through just basic email. We're not collecting a lot of information about our users. It's just their email, and then if they choose to, they can give us their institution. We're not asking for names. We may ask for their role in the company, but a lot of the most of the data that we gather from our users is anonymized, and we don't track or follow what is being searched on Mathilde's project. enabling the email-based login was important for users that sit in emails, sit in companies, and can't use any of the third-party providers. But the way we set this up was just the same way as for Google OAuth or for Facebook OAuth, namely a self-hosted email-based auth service called Portier. So this Portier service runs right next to the Grand OAuth proxy and right next to the admin API. They all run on the same local host in the same task in AWS Fargate, and they communicate through localhost. So that way, the kind of like the concerns here again are separated, and the setup is pretty easy to enable these different login mechanisms. So yeah, I can invite you to look at the Kong Proxy OAuth and look at the plugin code on GitHub. It's pretty simple. The thing additionally that I wrote is a simple Express.js server that runs this profile.materialsproject.org website. If you go to materialsproject.org right now and you log in, you'll see that workflow in action. A couple of things that we want to, we've always looked at ORCID ID, which is an identification for scientists, and that's a login mechanism that we were planning to implement in the future too. But with this system, it should be pretty straightforward for any OAuth provider. Okay, so let's pivot a little bit to towards the end of how we do unified observability. I've talked about the whole stack and how many pieces are involved. So it was very important to us to have visibility into the entire stack and be able to gather logs, search logs, in a performant way, and then immediately be able to react and diagnose issues as they come up. I've talked about how our different containers are running in AWS Fargate and the Fargate tasks. The application containers have the Datadog agent running in a sidecar container next to it. So a task could consist of different containers. As I said, there's the web container that runs in that task, the API container, but there's also a Datadog agent that sits in there in the sidecar and reports directly through VPC endpoints. So again, this is internal intra-region traffic that pushes data to Datadog. And we never had to set up things like specific things that basically allow traffic from a private subnet into a public subnet and then to the internet and then to Datadog. So all of this happens behind the scene on a very performant intra-network traffic. Traces, kind of, looking at where the Python processes might be not running well and stuff, are also sent to Datadog and allows us to dig deeper into our application. And then the logs on its own from the application containers go through what's called AWS file logs, basically just processing JSON logs, and also sends it through Datadog to the same VPC endpoints. Once it's in there, it opens up a lot of functionality for us. One, we can look at live tails. We can detect and generate metrics that we can track for a long time. This helps us with reporting to our funding agencies, and all the metrics you saw earlier, they all come from that same Datadog source. We can index and retain and search those for I think we've set up for a week right now, but the metrics are actually available for 15 months. So more aggregated statistics we can keep for longer, but then request by request logs we keep for a week, and can look at that 1 week back if we need to diagnose issues. And then we also back up and archive all those logs on S3 through Datadog. So as those Datadog logs are being parsed and tagged and analyzed, they also get pushed into S3 archives, and that allows us to later rehydrate these indexes back from archives. So if I needed to go back a year even and look at either metrics and generate metrics that I haven't kept track of, or if I need to look at a specific time where things might have been wrong and I want to do like a post-mortem analysis, I could reiterate that piece or that timeline in the logs and put them back into index and generate dashboards that way. This is what it looks like in our offices. So on the left, this is the Datadog dashboard in my office at Lawrence Berkeley Lab. This is up 24/7 and one of my daily in and outs that I look at. It has insights into the entire stack, even though you can't quite see things here. But basically, from left to right, it goes deeper into the stack. I can look at overall request stats, the error rates, our cloud costs, our open data traffic. So those are our S3 repositories with data, our callback times on the website, whether they are within margins, our health checks in general on the website, the traffic from different continents, our Mongo database, our API traffic, our CPU and memory usage in all of the tasks, our RDS and Elasticache database, and our email SCS services that sends welcome emails and stuff. So all of that is kind of within this one dashboard that I have can look at for different time frames and basically dig in as things go wrong. All these graphs are interactive and they're correlated with the logs that are being sent from the servers. So Kong is in here too. This two graphs on the left, that's Kong, but it's rarely making me any trouble. So pretty happy about that. Then we don't only have kind of this engineering view of the stack in Datadog, we also have observability for more high level. So this is a screen in front of in front of Christine's office. She's the director of Materials Project, and it kind of just goes through how many users we had that week, how much data was downloaded, what was the cloud costs, how many database documents were accessed, how much were our apps used, and how much were our APIs used. And then I also send out weekly reports to the stakeholders of the Materials Project that summarizes our uptime in that week and how many visitors we had and stuff. So this has kind of just become our just day-to-day operations. And in terms of a DevOps transformation, this has been a pretty big piece since we hadn't had any of this insights during our on-prem days and before we started transitioning to more cloud native products. We've also been accepted into Datadog's open source program as one of the first or the first project out of a scientific background. So there are other Datadog open source supported projects are, PyPy, for instance. And what you ask you or request basically is that you, as part of a open source sponsored project, you set up a status page, which has also been a good feature for us. So if you go to status.materialsproject.org, you'll see our current status, whether things are operational, and then some statistics, a different version of the same metrics from Datadog and graph differently about, are the error rates high right now? Is the website slow? Is it maybe just me, or is it actually a problem in the website? So this has helped a lot for us to also communicate incidents with our community. And all of this is automated. So it's not, I can go in and set incidents to be non-operational and set services to be non-operational, but in first order, this happens automatically through Datadog. There's monitors set up in Datadog that send a notification basically to this incident page and then set certain flags here from operational to degraded. So for instance, if our MongoDB is, if the CPU usage in our MongoDB is up, then this database flag would go to degraded and give people a little bit of an indicator that things might be slowing down, and it also sends me alerts if anything is going wrong. All right, just to tie things up a little bit, I've talked about open data sponsorship. So the overall goal of Materials Project in general is to be as open and disseminate as much data as we can. Like doing that in the cloud, of course, is always a budget question, but with the open data sponsorship, we've been able to take this part out of the equation, right? So this comes with free egress and free storage. We've been awarded 720 terabyte. We're like 10% into this, I would say right now, and we keep moving down our data stack closer and closer to the raw calculations that are in the hundreds of terabytes, and we are currently developing data products, based on HDF5, and on Parquet, that are efficient for cloud retrieval and also partial retrieval, and work well with our data processing pipelines. All of that is, in the service of FAIR. We want to be excellent data stewards in the future for machine learning and AI. So this is where, like, a lot of the traction is coming out from these days, that material scientists want to use more, not only our high level data that we disseminate through our API, but also our data products that are closer to, like, say, raw data or intermediate data products that are large, to train their models. And when they train those models, retrieving data efficiently is an important piece of the puzzle. Our open data repositories are all integrated with our Python client now. That was a seamless transition, and it actually enabled us to speed up our data downloads for some of the collections by a factor of 10. A lot of times what happens with scientist users of an API that are not familiar of what an API is and how it works is that they just want to go ahead and download everything. So they're not using really the query capabilities of an API and being, dedicated into how to make those queries efficient. They just kind of want to full download. So we've rerouted API requests that are full downloads just directly into our open data repositories, and that has sped up things significantly. It has also reduced the CPU pressure on our central MongoDB significantly. So that's an important piece of also our overall expenses, because MongoDB, the managed MongoDB database, is one of our most expensive pieces. And as we can reduce pressure on MongoDB, we can scale those differently, and then hopefully save some expenses. One thing that is currently in the middle of developing is our parsing pipelines and our general data processing pipelines. We are moving those to the cloud using things like Dexter and Dask to do parallel compute. That's where open data also plays a very central role, because all our parsing steps and our data outputs and data products that are being generated, they all go into open data. And then when we go and release a new version of our data, things get synchronized from open data into MongoDB for serving the API. All right. So that's the end of that story. I just want to kind of quickly summarize. I've talked about the Materials Project. It's the leading research platform and open source code for material sciences. We've been around for over 10 years. We've gone through a major transformation in the last, let's say, 5 years of our data and compute from on-premise DOE supercomputing resources to the cloud, and then everything as infrastructure as code. We've been running this in a production environment for 4 years now, 3-4 years, and we've been growing in that time and doubled our user base. Datadog was the piece that enabled us to do unified end-to-end visibility and also reporting to our stakeholders. Kong plays an important role to separate concerns and also route traffics, do authentication, do rate limiting without having to have that be in the developers, application developers' mind. Our open data sponsorship programs allows us to share as much data as we can possibly. And the final point that I want to leave with everybody is that everything I've talked about, our entire development and operations, is run by a handful of engineers. So the entire team you can see on the right, Christine is the director, Anubhav is the associate director, and the 6 people you see below is the engineering team that is about the size or half the size of the scientific PIs that we have in the project, principal investigators. So there's another arm of Materials Project that focuses on delivering science with the technology and applications that we as an engineering team develop. And then, me, Roshi, Tyler, and Aaron are permanent staff from Christine's group, and then Shreyas and Carlo are part-time support from the computing sciences at lab. So this group, over the last, in rotating participants, and the same size, has developed or delivered what you've heard about the last 20 minutes. All right. I think that's the end of the talk. I thank you for your attention and for attending this talk. I'm, again, Patrick Huck. You can reach me at phuck@lbl.gov or under my handle, tshalm. and Instagram and other stuff. So feel free to reach out if you have any questions. Thank you.
Thank you so much, Patrick. That was so good, so informative. I hope you guys enjoyed it. And if you have any questions, now is the time to ask Patrick. You can use the Q&A function. We were just asked whether this will be recorded. Yeah, we're currently recording and we will upload to our YouTube channel. And I will include the link right now in the chat so you can see it. And you will also receive a follow-up email with the recording, the slides, and some other resources. But if you have any questions, now is the time to ask before we wrap it up. Oh, we have one question, Patrick. Do you see the Q&A?
Nice. No, I don't have it up. Mind repeating it? Actually, I can. Let's see. Where's the Q&A?
Yeah. Can you see it
you
now?
might have to repeat it.
Yeah.
I might have to. Actually, no, I found it. Have you had
Okay.
situations where one of the Kong nodes has gone down? Yes. Going right at the heart of it. So what has happened is especially for long running services and depending on how I've configured the CPU and memory for Kong, there were instances where specifically the rate limiting would load so many entities into the Kong memory that Kong would just run out of memory. That would be a fast way of Kong running out of memory. A slower way is, just over time, more and more consumers being loaded into memory will just, sneak up on the max mem usage. So I've got this kind of long-term effect of Kong eventually running out of memory, and then that is over months, right? So this thing just runs months, and then there's like the short term where an intensive burst of requests that need to be rate limited by Kong just drives up memory. That eventually takes the node down, right? Once memory is gone, memory is gone. And luckily, most of the time, since there's two tasks running, this has been kind of mitigated by that, and because one node was always up. But one thing that I've done recently is that is making sure that the tasks in AWS Fargate are configured with health checks. So that task and AWS Fargate would notice that the Kong node is not responding anymore. To your second question now, is that something you're able to monitor? Yes. I have it, on the Datadog dashboards that I showed. There's CPU and memory usage, so I can see when things are sneaking up, and I'm getting notifications when on my phone too. I've got like 6 critical metrics. One of them is memory usage in each of our containers, and it'll kind of just blare at me if things are about to go broke. So I can get ahead of the curve, and I can try to take that node down, manually restart a new one, and that way have memory be freed again. That's kind of the pre-trust method. But as I said, I've also set up health checks in AWS Fargate for each of the Kong tasks. And once those health checks stop responding for a certain time because they ran out of memory, then a Fargate would take care of spinning up a new task and spinning that old one down. So that adds resiliency, a combination of those two things. So good end-to-end visibility through Datadog combined with health checks in AWS Fargate. Hope that answers the question.
Thanks, Patrick. Let's see. Any last questions for Patrick before we wrap it up? Oh,
Have you
one
added
more.
auto-scaling to the infrastructure? Yes. We haven't needed auto-scaling as much as I thought we need, but it's definitely in there, especially for the website. So since the website is based on Plotly Dash, and it sends callbacks to the backend for every HTTP request, basically, or even elements on the website, there's a lot of CPU that is kind of being handled by the backend instead of the front end or the browser on a computer's machine, and a computer CPU. So that fact sometimes can spike CPU in our backend services, and that's where auto-scaling comes in. So I've set up ways that if CPU is elevated for a certain amount of time, it would just add tasks to that website as service and take care of that. It has never gone past doubling our tasks because these things happen when people run workshops, right? So basically, a professor at a university would run a workshop, And this 50 students in that class would run the exact same command and the exact same time. And that's unlikely usage during standard operations, right? But it happens, and most of the time when people give us a heads up, I can spin up a few extra tasks to avoid that. But that's where autoscaling has helped us. It's not as often as you would think, though. So we've been pretty fine with just having 2 tasks for each of our services and have redundancy that way. We didn't need to go into more. Final question. Have you considered using AI to analyze the logs and help with autoscaling? Yeah. Oh, thanks for the size of your team. You're doing awesome. Yeah, it's coming up more and more. It's not been part of our design recently, but we're thinking about ways of how AI could help us. It's not quite a direct answer to your question, because we haven't, gone into AI analyzing logs. We rely on Datadog to find. Datadog has Watchdog, I think they call it. So that's basically them continuously analyzing logs and alerting you to if things are out of the ordinary. That has helped here and there to bring things up, but just having the dashboards and the alerts set up on Datadog has helped me stay ahead of the curve for those things, and then even scale up manually instead of using auto scaling sometimes. But in terms of AI, we're actually thinking more about how can AI help us do documentation. That's actually more at the front of our thoughts right now, in the sense that we have a lot of we have a big community where people answer forum questions, and we're looking at ways of how AI or ChatGPT could help us summarize those and then maybe send this to people in our group, to postdocs and grad students that could review the summary of those closed forum threads and integrate it into our official documentation, and that way close the circle with search engines and other things. So it's just kind of an extended answer to how we're thinking about AI right now.
Thanks, Patrick, and thanks, Michael, for asking the questions. We're at the hour, so we're going to wrap things up. Thank you, Patrick, so much for being a speaker today. We loved having you here. Hope you will join us again. And thanks, everyone, for joining us and staying until the end and asking all those amazing questions. You'll receive the recording soon, so you can rewatch it if you'd like, and some other additional resources. I put in the chat our next Tech Talk is on the 27th, if you'd like to join us. And with that, have a good day, have a good evening, whatever you're joining us from, and I'll see you soon.
Thank
you. Bye,
everyone.
everyone.
Bye-bye.
Bye.